And we'll turn to example 2. And example 2 is where the review of transformations really begins. Okay, the question in part A, it says, use the graph of y equals 2 to the x to graph, we'll put this in blue, square y equals 3, 2 to the negative x plus 2. So a couple of things. It says use the graph. What's often going to be the case is you are going to look at what you want to graph, and you have to pick out of here, oh, the x is in the exponent, it's an exponential graph. What kind of exponential graph am I moving around? What's the base for the exponent of x? The base is 2. So this question tells us to first look at y equals 2 to the x. But most of the time, you would have to pick that out yourself. Not very hard. You see the x in the exponent and just ask, what's the base? The base is 2. So our regular 2 to the x graph, well, all regular exponential graphs have an asymptote at y equals 0. They have the point 0, 1. And since the base is 2, this one has 1, 2. So there's my 2 to the x graph. They did not start us off with an easy one. They started us off with an exponential graph that includes a special note from transformations. Because if we look at things, the 3 is outside the function. That's going to be a vertical stretch. The negative is inside the function. That's going to be a horizontal reflection. And the 2 is also inside the function. It's going to be a horizontal translation. But we had a special note that we wrote down that said when you have a horizontal stretch reflection or compression and a horizontal translation, you always have to first write it in factored form. So I have to factor out that negative first. And that 2 is actually going to move it 2 to the right and not 2 to the left. So that's the number one mistake that happens in these ones. We move it in the wrong direction. The other reason that we could have done all of our exponential graphs in our transformations unit as well, but I felt you had enough graphs in that unit. And adding the transformation graphs makes it a little bit complicated because there's so many of them. There's the 2 to the x, 3 to the x, 4 to the x, 5 to the x. You can have any base. The other thing that makes an exponential graph a little bit tricky is sometimes students get confused because there's a number, right? The number 2 is in here, but that's not a transformation. The number 2 is part of your parent graph. So one thing that I find helpful is, I did my parent graph in green. I'm going to put a box around the 2 and the x, sort of to remind myself that's my parent graph. As far as what's happening then, I've got a 3. That 3 is a vertical stretch. I'm going to multiply my y values by 3. Next, the negative. That's a horizontal reflection. I'll multiply my x values by negative 1. And then the 2 is a horizontal translation going 2 to the right. So I can do my labeling just like we did in our transformations unit. Then I'm going to take my 2 key points from my green graph, 0, 1, and 1, 2. Remember in transformations that we always did stretches and compressions first, then translations afterward. So we have y is getting multiplied by 3 and x is getting multiplied by negative 1 for our stretches and compressions. And for our translations, we just have the 1. It's moving 2 to the right. So now I can do the mental math. I'm going to have 0, 3, and negative 1, 6. move it 2 to the right, 2 comma 3, and positive 1 comma 6. Those will be my new points. The other thing that we're going to do with all of our exponential graphs is see what happens to the asymptote. And since the asymptote starts at y equals 0, we really only have to do one arrow, because any kind of multiplying, if you multiply y by 3, and it was at 0, it's not going to change it. No multiplying anything by 0 is going to change it from equaling 0. The only thing that would change a horizontal asymptote is if it got moved up or down. Can you see if something's horizontal and goes on forever, and you moved it left and right, it's exactly at the same place. But only moving it up and down is going to change the value. Are we moving things up and down? No, we're going 2 to the right, so our asymptote is going to stay. So now we've done our setup. We are very close to graphing. Another thing I want to point out, because you are going to be tempted by this, okay? I find putting the green boxes around the 2 does 2 things. One, it reminds you that 2 to the x is the graph, which we talked about already. 2, it reminds you about order of operations, because I'm going to tell you, you are going to be tempted by this. You are going to see 3 times 2, and your brain is going to be like, I'm so good at math, 3 times 2 is 6. Okay? Can you see yourself seeing 3 times 2 and be like, oh, I feel good, I'm going to write 6 right away, I'm so smart. We have to be careful because of order of operations. In this equation, you have exponents and you have multiplication. In BEDMAS, order of operations, exponents happens before multiplication. So before you would ever be allowed to multiply the 3 times 2, you would have to do all of this math first. And because there's an x there, you can't actually do that. But you're going to be tempted sometimes to go, oh, but 3 times 2 is 6. But that's not allowed because of order of operations. So sometimes putting that green box around there sort of helps remind you, oh, I have exponents here. I can't do the 3 times 2. Now that we've got all of our new points, we can start drawing our asymptote. Is going to be at y equals 0. Labeling our points, we've got 2, 3, 1, 6. If I connect those, oh, it's going down, so it has to go towards the asymptote this way. Put arrowheads on our graph, and there is our final graph. So I'm going to get you to try one on your own. Maybe I'll just do it on the same page so that you can see. If you're copying this down still, you can still see it. I would like you to graph y equals -5 times 3 to the 2 x plus 4 minus 1. Start putting out the answer. You can keep working on yours and check it after. Just graphing the 3 to the x graph. check how you did. So your asymptote gets moved down 1. The points that you find on your new graph are -4, 6, and -3.5, -16. Draw the shape of the graph towards your asymptote. And this is just a basic review of your transformations unit. Now you still might have space on this page, or maybe you have space on page 346. If not, we're going to do 2 more examples. There's space on page 357. Is it all right if I change? Everybody has checked their work on these ones? Okay. So first of all, I need you to take out your calculator, because we are going to get introduced to a new number. A number some of you have never seen before. Some of you might have only heard about it in ancient Rome. The number is E, not to be confused with the letter. I know, like, be a little bit creative, mathematicians. We learned a new number today. We learned the number E. Find the number E on your calculator and push enter. The number E is like the number pi. It's a decimal that goes on forever. But you know that pi is 3.14. At least I hope you've heard of that one before. Find out what E is to 3 or 4 decimal places. See if you can find it on your calculator and push equals. All right. So sometimes it's a little, and then if you want E by itself, you push the 1. There it is. Crazy number. Yes, found it. Some calculators you have to put the exponent of 1 in. Some of them let's just let you do E. Not quite. Just so you can use the exponent, you put 1 in there, or you can just your button's right there. All right, so we're finding it. Some of you have got the value already. And it sure looks like it has a nice pattern. It's deceiving that way. It sure looks like, oh, does it just keep going 1828, 1828? No. It goes crazy after that. It helps me memorize the first 9 decimal places, but it doesn't keep going 1828. It, just like pi, goes on forever with no pattern that repeats itself. And the number E is extremely important in calculus. And in calculus, it's extremely important in exponents. So we are going to graph y equals e to the x, which isn't hard. It's the same as graphing 2 to the x, 3 to the x, 5 to the x. But instead of labeling 1, 2, you now can label 1, e. It still would have 0, 1, still would have an asymptote at y equals 0. And we'd also be able to graph all of our transformations unit with E. You would recognize, okay, my parent graph is e to the x. What do I have here? I have a 3 in front. That's going to be a vertical stretch. I have a -2 in the exponent. That's going to move 2 to the right. And the -1 is going to move it 1 down. And we do the same thing we would have done before. Start off with our points, 0, 1, and 1, e, and do the transformations. And this is a little fun. What would happen to e if you multiplied it by 3? This is really enjoyable in the English language. because you would get 1 comma 3. Not just 3. 3e. 3e. Yeah, nice. And then when you go 1 down, you'd have 3 comma 3 minus 1. I think that's going to be my new favorite number. Someone says, what's your favorite number? I'll just say 3. They like 3? No. 3. Maybe it's so confused. Now, graphing this, you would have to draw in your asymptote. 2 comma 2 is easy, but 3 minus 1, you'd have to estimate. So 3 times e would be like 2.7 times 3, about 8.1. Subtract 1 off that. This point is approximately at 7.1 something. So you just have to roughly put it where it would be. And it has the same shape as all of our other exponential graphs as well. So questions you can circle now are 10 and 13.